It's okay for you? Okay, so please have a seat. We are going to start our session. Hello, everybody. We are going to start the session this afternoon. So this afternoon, we will focus on monitoring and prevention and remediation in different settings, in hospitals, in homes, at work. And first, we will have a presentation by Raquel Sabino from Portugal. And hello, Raquel, do you hear me?
Hello, yes, perfectly.
Hi, Raquel. Very nice to see you.
Hi.
We see you.
You too.
It's perfect. So thank you very much for being with us and to give a talk on an overview of indoor and outdoor exposure to fungi. This morning, as you have seen in the program, we have discussed fungal exposure in asthma, in COPD. Then we will see monitoring and remediation. But please, you can start.
Okay. So good afternoon, everyone. First of all, I would like to thank the invitation to give this talk. Special thanks to Jean-Pierre Gangneux and to ECMM for organizing such an excellent symposium. Unfortunately, it was impossible to me to be in Rennes with you, but it is always a pleasure to join you, if only by Zoom. So today I'm going to give you an overview about indoor and outdoor fungal exposure and possible implications in human health. So these are my disclosures, and during this talk I will approach the following issues: exposure to environmental fungi versus fungal disease, which fungal species are more frequently associated with fungal exposure, and how we may monitor them in the environment, indoor and outdoor exposure to fungi, and I will focus specifically on high risk and low risk environments. And finally, I will also talk about climate changes as contributors to indoor and outdoor fungal exposure. As Martin already said yesterday, there are about 5 million of estimated fungal species, but only about 300 are described as frequently causing infections in humans and animals. So the majority of these pathogenic or potentially pathogenic fungi occur naturally in the environment, and we have been observing the emergence of an unprecedented number of environmental fungi as major cause of diseases. An interaction between the pathogen, the host, and the febrile environment is mandatory for the occurrence of fungal disease. Exposure to environmental fungi is always occurring, whether it occurs indoors or outdoors, in leisure activities, in the workplace, agricultural activities, food processing, industry, in home, or even in hospitals. So, in that sense, fungal exposome is defined as all the fungi that we are exposed to. Fungi are ubiquitous in the outdoor and indoor environment, and originating in both natural and anthropic sources, as soil, water, living or decaying plants, animals, food, industry, furniture, among others. And they are collectively denoted as external fungal exposome. This external exposome is influenced by factors that include, for example, the climatic conditions or the presence of specific contaminants. The internal exposome consists in the fungal part of our microbiota, the microbiota, and comprising fungi inside of the human body or in its cutaneous or mucosal surfaces. And it's influenced by individuals' biological factors such as metabolism, diet, physical activity, and infections, for example, as you can see over here, and as it was already discussed. External and internal exposome interact every time, for example, by inhalation and ingestion of fungi or fungal fragments. During and after exposure to fungi, several adverse health effects may occur, and they can go from mild, as running nose, sneezing, itchy eyes, to severe infections as sinus infections, pneumonia, or even invasive infections causing high mortality or morbidity rate. The severity of the symptoms will depend on the associated features of the exposed person, as gender, genetic background, habits like smoking, medication, previous respiratory conditions, or the immunological status. On the other hand, the severity of these adverse health effects will also depend on temperature, humidity levels, presence of dust and particles, which will influence the fungal loads in the air and even the fungal species or certain specific strain. The nature and abundance of the dominant fungal spores in a certain environment exhibit marked variations, and to monitor them, it is important to emphasize that only using a multi-parameter approach, using different sampling procedures, sensorial and methods of analysis, we can characterize the bioburden because the real exposure results from exposure to complex mixtures of microorganisms, molecules, and particles. So, in order to a better characterization of the fungal exposome, for environmental sampling, a combination of active and passive sampling methods should be properly adequate and applied to each environment that we want to study. Then, culture-based methods and molecular tools, either by targeted real-time PCR or metagenomics, should be used in parallel to overcome limitations of each method used. This is the the ideal scenario. And afterwards, after obtaining our fungal isolates, we may also evaluate other parameters such as the resistant profile. We can study isolates deeper by molecular identification of the species, for example, for detect cryptic species, and go even deeper doing whole genome sequencing of specific strains or genotyping some isolates. During this talk, I will focus exposure specifically to some fungi as Aspergillus, Candida, Mucorales, Cryptococcus, and dimorphic fungi. All these fungi are highlighted by the WHO as priority fungal pathogens, as Anna already mentioned yesterday, and we will now discuss in more detail their environmental niches, their importance as etiological agents, and how indoor or outdoor exposure to these fungi occurs. Some of these fungi were already mentioned in the presentations done so far, but I hope to give you some more insights on them, and I will wrap up some issues already discussed as well. So, we are going to start talking specifically about Aspergillus. As previously mentioned, the global burden of Aspergillus diseases is high. Aspergillus conidia are very resistant, produced in large amounts, very easy to dissociate and disperse in the air and easily inhaled. And more than 80% of Aspergillus-related conditions are caused by Aspergillus fumigatus because its conidia are small enough to traverse the terminal respiratory airways and to reach the pulmonary alveoli. Aspergillosis is a spectrum of diseases that consists in allergic, chronic, and invasive forms, and the Aspergillus impact on human health will depend on the host immune system, on the concentration of conidia in the air and inhaled, on previous pulmonary lesions, and on strain virulence. This latter includes the production of mycotoxins and antifungal resistance, for example. Given the importance of indoor and outdoor exposure to Aspergillus, I'm going to discuss a little bit the prevalence of Aspergillus in highly and low contaminated occupational environments. So, in a study performed by Viegas and co-authors, they have compared different settings where a higher load of fungal contamination was expected, and they analyzed the prevalence of the total fungi found, the gray bars over here, and the proportion of Aspergillus found, that these red bars here. So they analyzed air and surface samples and concluded that wastewater plants, waste sorting plants, and poultry and swine farms were the occupational settings with the highest Aspergillus load. Focusing on this specific environment, as you can see in this study developed in poultry and swine farms, we have found high Aspergillus load in the air, surfaces, and the floor coverage, which was constituted especially by straw or by wood shavings. Then we aim to perceive if this environmental Aspergillus contamination was affecting the workers' health. And with that purpose, we analyzed 80 workers from these settings, and the incidence of diagnosed asthma was 8.8%, and the occupational asthma was 5%. Additionally, workers without asthma, in workers without asthma, there were there was higher prevalence of respiratory symptoms that improved significantly when the workers were away from their jobs. In this study, the authors present the airborne concentrations of mycotoxins found in different occupational settings, and as you can see, animal housing and food and feed industry were the settings where aflatoxin A and oterotoxin were detected above the concentration of no toxicological concern for mycotoxin exposure, which is this gray line over here. Returning to our case study in poultry and swine farms, we performed the detection of aflatoxin B1 in the serum of these workers, and 53% of the swine farm workers and 55% of the poultry workers were positive for the detection of AFB1. Since no information is available regarding the AFB1 background levels for the Portuguese population, a control group was included in the study here, and none of them were positive. This suggests that possible the occupational exposure was due to inhalation and not ingestion. So returning to our study, we realized that waste sorting plants were the settings where the high levels of Aspergillus contamination were found, and so we analyzed Aspergillus fumigatus from these settings, and we realized that we found really some isolates with mutations in CYP51A, and the mutation most frequently found was the TR34 L98H, which represents multi-azole resistance to these isolates. Interesting, these isolates were detected in the filtering protection devices of the worn by the workers in these plants, waste sorting plants. So it was very interesting to realize this exposure. As previously mentioned, the resistant mechanism associated with this mechanism of resistance, TR34, is an induced azole resistance in agricultural settings due to the usage of agricultural fungicides for crop protection and to preserve material from fungal decay, leading to what we think it's a very concerning situation and a public health threat. In fact, in these environments, workers are highly exposed to fungi like aspergillus because they inhale high amounts of fungal spores, including antifungal resistant ones. And they are exposed to aerolized mycotoxins as well. We also detect azole-resistant Aspergillus fumigatus with the TR34L98H mutation in sawmills environment. And in this case, in addition to environmental use of azole fungicides for protection of spruce and pine fields, sawmills processing resinous woods frequently use azole fungicides to protect wood from phytopathogenic fungi that cause wood deterioration. So here we propose an algorithm to the fungal sampling and to detect azole-resistant aspergillus isolates in occupational settings. The risk of acquiring aspergillosis-resistant isolates included has to be minimized, not only at work, but also at home, as already mentioned by Malcolm today morning, and avoiding moldy and dusty environments, and also avoiding activities that may lead to the exposure to elevated concentrations of conidia, like gardening or composting. The usage of protective equipment is also a major recommendation, especially to immunocompromised patients. In case of specific suspicion of a clinical case, an inspection of the home environment can be a plus, as discussed today morning. We may also approach Aspergillus exposure in low contaminated environments as hospitals should be. However, several nosocomial outbreaks caused by Aspergillus are described and are caused essentially by flaws in the hospital water system, in the HEPA filtration system, by construction or demolition work in the hospital or nearby. And we can also consider other sources of Aspergillus contamination in hospital, like food, plants, fabrics, for example. In a study performed by our research group, we analyzed air and surfaces from the bone marrow transplant units, hematology, oncology, and ICU wards of one of the biggest hospitals in Portugal. Aspergillus was the most frequently genre found, and the Aspergillus isolates were sequenced, and we have identified 25 different species with a high percentage of cryptic species, some of them with lower antifungal susceptibility. So regarding the exposure in hospital environment, it is important to understand the local epidemiology and see what happens in different hospital wards housing high-risk patients in order to achieve a better management of the risk of infection. Going deeper in the study of Aspergillus fumigatus isolates found in hospital environments and other sources as clinical samples, we have genotyped these isolates using microsatellite markers, and we aim to distinguish epidemiological related isolates, to identify prevalent genotypes associated with specific diseases, and to determine possible routes of acquisition and possible reservoirs of specific strains. This method is very discriminatory. It's a high discriminatory power with about 99%, and allowed us to realize that the majority of the multilocus microsatellite genotypes were unique, as you can see, for these dots, all isolated dots. But interestingly, some isolates shared exactly the same multilocus genotype, and some of them were from different sources. And just to give you some examples, as you can see here in green, the same multilocus genotype was found and shared by 4 isolates collected from air, surfaces, and soil of the same hospital in different years and from different wards. Here in blue, you have the same multilocus genotype found in a clinical sample and in the air. Then in orange, you have 2 isolates that share the same multilocus genotype, both from clinical sources, but one is from an animal source and the other one is from a human source. Finally, here in pink, we have 4 isolates that share a very similar multilocus genotype collected from air, soil, human, and animal sources. So, in this study, some isolates from different sources appear to be closely related, some of them with exactly the same multilocus genotype, highlighting the relevance of Aspergillus fumigatus in this One Health context. This One Health context does not end with Aspergillus, and we can apply it to a high number of fungi to which we are exposed to. An example of that is Candida. Candida transmission can occur by 2 different routes: endogenous transmission, when the patient develops infection caused by a strain that was already a colonizer of that patient, as occurs with Candida albicans, or by exogenous transmission when the patient develops infection with a strain transmitted by contact of contaminated hands, surfaces, or materials. And this is the case of Candida parapsilosis or Candida auris. Just to give you an example of how the environment can be crucial for the onset of Candida infection, I'm going to present you another study performed in an hospital where air surfaces and hands of healthcare workers were screened for the presence of Candida parapsilosis. Also, by microsatellite genotyping, it was possible to follow the route of transmission of specific strains. So, in this case, for example, this strain was found in a nurse's hand in January. Then we have found the same strain in April in 2 different surfaces of the same ward, and in May, this exactly same strain with exactly the same multilocus genotype was isolated from the blood culture of a patient hospitalized in this same ward. This same situation may occur with Candida auris that has emerged as highly drug resistant and also associated with several nosocomial outbreaks due to its long time survival in surfaces and resistance to disinfectants. Its appearance and spread have been linked to climate change. The thermotolerance and allotolerance of this species result in adaptation to different environmental niches and subsequently to humans' infection. When we talk about environmental exposure to fungi, we need to talk about Cryptococcus. Exposure to pigeons' excreta may lead to Cryptococcus infection, especially in immunocompromised patients. However, Cryptococcus gatii also causes cryptococcosis in immunocompetent individuals, and it is usually found near trees like eucalyptus. Until recently, the geographic distribution of Cryptococcus gatii was thought to be limited to tropical and subtropical areas. It was hypothesized that the increased temperatures or other changes in the environmental niches may select strains of Cryptococcus with an enhanced virulence feature as Cryptococcus gatii, sensu stricto, or Cryptococcus deuterogatii. And this may explain the spread of this fungus to more temperate climates leading to the outbreak in Vancouver and further expansion to the USA. Other fungi to which we are daily exposed indoor and outdoors are the Mucorales group, and its transmission may occur by inhalation, ingestion, or traumatic inoculation. The majority of these fungi affect especially the immunocompromised patient. However, some of them, like these ones over here, can cause infection in immunocompetent patients after trauma or injury. Some of those cases are associated with natural disasters as tornadoes, tsunamis, earthquakes, and floods, among others. These infections occur because during these extreme weather events, people get hurt and suffer skin injuries with the introduction of the etiological agent directly in the skin or in the subcutaneous tissue. Even a part of these cases caused by Mucorales. By Mucorales, the rise of fungal infections is frequently associated with extreme weather events. For example, events like flooding can lead to an excess of indoor moisture and mold growth, and therefore, as Malcolm already mentioned, damp and moldy environments may lead to allergic symptoms in people and animals, or even to more serious infections. Also, infections caused by dimorphic fungi are becoming more common and are increasingly reported in non-endemic regions. Coccidioides, Paracoccidioides, Histoplasma, Blastomyces, Talaromyces, and Emergomyces were considered as having restricted geographical distribution due to their inability to proliferate outside their specialized ecological niches. However, increases in migration and traveling all over the globe, as well as the increasing in frequency, intensity, and duration of extreme weather events, led to the spread of these fungi, of the spores, and consequent changes in the epidemiology of these fungal diseases. To wrap up, our changing environment is therefore caused mainly by changing in land use patterns, use of antifungals in agriculture, and increasing global warming or increasing extreme weather events. This led to epidemiological shifts that will likely expose us to fungi which humans have never interacted. More humans, animals, and plants will become at risk for fungal infections and for mycotoxin exposure as well. The prevalence and diversity of microorganisms will undoubtedly change, and these shifts have been already observed with endemic fungi and with the emergence of novel fungal pathogens to humans, animals, and plants. I could not finish this talk without mentioning the TV series The Last of Us. In the beginning of the first episode, it was discussed the problem of the rising temperature and how it could increase the number of fungal infections. And although all the fantasy associated, this series made everyone think about fungi. Also, for the first time, a clinical mycologist was the star of an episode seen by millions of people. So I guess that all of us felt a moment of glory at that time. Anyway, my take-home message is always think fungus and consider new etiological agents because we are subjected to fungal exposure in every indoor and outdoor environment, and that exposure can affect us in very, very different ways. So thank you very much for your attention, and I'm available to further questions.
Thank you very much, Raquel. It was
Yep.
a very nice introduction for all the following talks, regarding monitoring, regarding prevention and remediation. So if we have one question, but perhaps it will be the same focus as the following talks? No? So, thank you very much, Raquel. It was very nice to have you with us. And,
yeah, thank you so much.
And we will move to the next presentation with the tools for epidemics investigation. Is Alexandre with us?
I'm here. Hello. Hello, everyone.
Hello, Alexandre. How are you doing?
I'm just trying to share my screen.
Okay.
So I would like to say hello to everyone. Happy to be not really in presence with you, but at least to give this talk remotely.
So Alexandre Alanio is a professor of medicine in Paris, in Saint-Louis Hospital, and working also at the Pasteur Institute. And Alexandre, you can start on the tools for epidemics investigation. Thank you very much.
Thank you. Is it okay with screen presentation?
The taxi will be ready at 5 minutes before. Yes, 5 to 3. Yeah. 5 to 3. So, thank you very much for coming. Thank you.
And so I will pause at the end of the talk to explain a little bit more what are the advantages of some specific techniques. So first of all, what is an epidemics? What is an outbreak? So you start with an index case, and then you have many cases that appears, and the main point in the analysis you will have to do is what kind of geographical area or what kind of time you will have to take into a consideration to investigate. And so these are moving values here that you can consider differently in different settings. And obviously, what we will all do here is to consider at least this event, those who are temporally related and geographically related at first, and then to expand to more distant isolates or cases during the outbreak. So if you consider another way to report those cases can be this in terms of timing, the time here, and the number of cases. And the different colors here are different geographical areas. So you can have an increased number of cases and then a decrease and see the real evolution of the number of cases in a specific geographical area. But if you change the geographical area, you would be able to see different things. And so you have to consider also the place and how big is the focus you have to put on a specific place or outside to look at the outbreak. So first of all, what kind of tool do you need? So you need this kind of tool. This one is a very interesting tool. Do you know what kind of tool is it? What is the name of this one is Curiosity. This one is on Mars. And so Curiosity is very important to manage an outbreak. You have to be open-minded, meaning that all the possibilities have to be explored to understand the initiation of the outbreak and to understand the transmission you can have between the different cases. So the second tool you need is something very important, and it's not really a tool per se, but it's something that is very important because it allows you to detect the cases and to have in mind and to have on a regular basis the different cases you have in your hospital is a weekly case review meetings. And so I think it's very important in a very big hospitals you have these kind of meetings that have been implemented, and they are useful for different things. They are useful to discuss together with clinicians, with pharmacists, with hygiene people to manage those fungal infection cases. But it's very important also for all those people who are participating to detect mainly linked cases by reviewing those cases on a regular basis. So that's what we are doing, for example, in my hospital. So all the doctors from the lab are present, the antifungal stewardship people, the physicians, the pharmacists, and we are reviewing weekly all the cases of invasive fungal disease and also the suspicions of invasive fungal disease associated with starting of antifungal therapy. We have also specific meeting which can be called the Aspergillus task force in our hospital, including work technicians and hygiene doctors. So we are reviewing also all the cases of aspergillosis every 6 months to see the epidemiology, the number of cases, and to see if there is local problems that have to be solved or fixed to avoid aspergillus contamination, for example, from the environment. The third tool would be to have to be in relationship with the national reference center. So here in France, we are lucky enough to have a fully funded national reference center for invasive mycosis and antifungals. And the missions of this national reference center is to give expertise for identification and genotyping, to give stewardships in terms of diagnosis or therapeutic management of the patient, to do surveillance epidemiology, to have values every year of the different repartition of the different pathogens in different settings, and it's not only based on the microbe, but also on the patient and the cases. Meaning that we at the reference center we are asked to do surveillance on the bug, but also on the patient characteristics. And then the fourth mission of this is to give an alert and to discuss with the authorities, the national and the European authorities, to be able to detect some abnormalities in terms of occurrence of cases. And that's a very nice structure that can be that is available to discuss with all the French centers who are dealing with invasive fungal disease. And here at the reference center, we have also weekly meetings who helped us also to detect some abnormal events in terms of transmission or increased incidence. So this meeting is based on engineers, technicians, the director and the deputy directors and the collaborators are participating to these meetings, and we are reviewing all the cases of invasive fungal diseases associated with the strains that we received at the reference center and we are handling. And so we are discussing at this meeting about the underlying disease of the cases, the identification of the strain, the UCAST antifungal susceptibility testing profile, and the therapeutic and diagnostic management. So with this kind of meeting, you can also approach and really detect early some specific events. And the goal of our surveillance at the reference center will also be to have automated analysis of increased number of cases and detect abnormal situations in terms of incidence of fungal cases. So the first tool you need is to discuss with the clinicians and to be sure that the clinicians will investigate also the patients, and that is decided in the specific meetings where you have a multidisciplinary meeting. But if you don't sample, you will never know exactly what happens. Meaning that to investigate this kind of outbreak, you need to sample the patient and to do it in optimal manner. And taking into account the cost that represent this. But if you are not sampling, you will not be, you will have a very blurred picture of the outbreak. So that's the first point. Then in terms of microbiology, you need, as a microbiologist facing this kind of outbreak, you need to understand the link between the infections through the characterizations of the strains to know what kind of strains you will face and if a specific strain is transmitted from a patient to another. So the first step to focus on the real epidemiology or the real incidence of the event is to identify the fungal isolate. That's very important. It's very easy to say. It's a very basic process in microbiology, but still you need to do it accurately to be sure that what you are facing is coming from the same bug, meaning the same fungus, the same genus and the same species. And how to do that? So you cannot really do that by morphology or just by looking at the color on chromogenous media or by identification gallery, because you know now that you can only achieve genus or species complex level of identification. But now with Malditoff mass spectrometry and improved libraries, databases of associated with this device, you can reach species level identification. And of course, you can verify those by multi-locus sequencing to be sure that the identification is the same when the database of Malditoff may not be accurate enough. So that's the first point, to be sure that you have the same species responsible for the cases that are linked. Then you go to a second step, and the second step is to establish the relationship between isolates. Meaning that you want to know if you are facing the same genotype, meaning the same individual, fungal individual within the species. Because this same genotype would be the spread of the same clonally amplified organism through mitosis. And so to do that, you need to have genotyping tools. And sometimes for some specific bugs, there is no genotyping tools available. And so you need to use different tools and different tricks to have an idea of the genetic relationship between the isolates. And so many genotyping tools have been developed over the last 50 years. And I will give you an overview of this old methodology to finish by the new ones. So the first one, I won't go into too much details because you may have heard about them. First, you have RAPD, which is randomly amplified polymorphism DNA, which is based on the random amplification of repeated sequences and based on primers designed for those repeated sequences that you can have all along the genome, that gives you an overview of the presence of those repeated and the location of those repeated sequences. And so, for example, if you have this kind of example between isolate B and isolate A and B, you'll see that you don't have the same number of fragments generated by this specific PCR, giving you a different profile in terms of fingerprinting here. And with this, you are pretty sure that the isolates you have are different. So this has been used for different things, and I give you here an example of a paper I like about cryptococcosis, and they used RAPD to prove that the crypto that have been recovered from patients with cryptococcosis coming from Africa were actually genotypes of cryptococcosis that you can find in the environment in Africa, meaning that you have a very long latency period between exposure of crypto from the environment and reactivation of cryptococcosis in another country. And so they use their RAPD to demonstrate this in migrant patients. Then you have RFLP. RFLP is restriction fragment length polymorphism with a specific probe of repetitive element, and then to have southern blot hybridization after restriction enzyme, allowing you also to identify specific restriction sites and give you different profiles in terms of electrophoresis to compare the DNA, the presence of those specific loci and mutations at those loci in the different isolates you are investigating. And so basically what you are doing then is to migrate this DNA that is digested by this enzyme and then identify the different profiles of the isolates. Then you have another one that can be that is called SSCP, which is a single strain conformation polymorphism. So after amplification of specific fragments, you can design, you do migration on the gene in specific conditions. And if you have mutation in the gene, you will have a different migration, even caused by a single mutation that will give a different profile and a different migration distance as compared to the control. And you'll see here from this example, the presence of different mutations in pneumocystis jirovecii. Then what have been done more often in terms of genotyping is using multi-locus sequence typing, which was developed at the very beginning for bacteria investigation. And in fungi, we did the same. I give you here an example. So basically, you have to choose between 6 and 8 different targets, mainly in reference in, let's say, housekeeping genes. And then you sequence those genes and you appreciate the diversity and based on the number of SNPs you can get from those sequences. Here is an example of the MLST scheme for pneumocystis jirovecii, which is based on nuclear genotypes and mitochondrial genotypes for historical reasons, but non-optimal reasons. So basically, usually we are using only nuclear genotypes. And you do Sanger sequencing, and then you can appreciate if you have mutations at specific locus and if the organism can be related, meaning in our context to know if it's the same or not, if you have the same sequence based on different markers or not. And another one that has been developed more recently based on the human genotyping method is STR typing, which is tandem repeat, short tandem repeat genotyping with a specific methodology based on the analysis of the length of the amplicon, because those repeated elements, those repeated sequences can be amplified or contracted in different organisms and that are specific of these organisms and in the end quite stable in a specific organism. So here I give you an example of the short tandem repeat genotyping methodology we developed for pneumocystis jirovecii based on 6 nuclear markers that are markers distributed along the genome, allowing to determine the genotype and to compare isolates from the other ones. So in the case of pneumocystis, there is no isolates, but it's only DNA extracted from respiratory specimens. So those are all genotyping methods. The resolution of those methods is not perfect, so it's perfectible for all these methods, and the costs are quite reasonable. But the good point is that you don't need support for analysis of the results. So you can do that if you have this method available in your center. You can do that in first intention, meaning the first point is to know which isolates are identical to each other, to the other ones. And if those are different, so you are quite sure that those are different. If you see the same profile with this kind of methodology, then you have to apply another methodology which is more resolutive, more sensitive to variations. And here we will discuss about whole genome sequencing. But for whole genome sequencing, the costs are more important, but it can be decreased if you have a lot of isolates to investigate. And the main problem is that you need support for bioinformatical analysis and to analyze the results. But it depends on also the presence of a reference genome. If you don't have a reference genome, it can be more complicated to get analysis of, the relativeness of those isolates you have, and it can be longer because you have to use different methodology. But still, now you have different automated tools that you can use from the web to help you to compare the isolates based on the whole genome. So I give you just two examples of investigation of outbreaks. So the first one is here an outbreak of mucorcercinurides in a wound in a burn ICU, responsible for wound mucormycosis. So on the lower panel here, you have the six cases we faced over a period of 2 years in our center. And what you can see here is that patient 1, 2, and 3 are hospitalized at the same time, and that's the time where we investigate this outbreak with 3 patients having the infections at the same time in the same unit. And so to investigate the event, we investigate, of course, the isolates from the patients from the same unit, but also isolates from other units in the hospital, and also isolates from other burn units in France, just to have an idea of the diversity of the isolates we can obtain with different methodology. So we first did very basic ITS, 28S, and RPB1 sequencing to have an idea of the, let's say, the identification. So all belong to Mucorcercinurides species. And based on the diversity of the 3 genes, which are not really considered as genes, let's say housekeeping genes of MLST, but based on those 3 genes, you can have an idea of the diversity. We did not really understand the dynamics of the transmission of the bugs, with some that were supposed to be quite identical and some were quite diverse. And so we went to whole genome sequencing to better understand the relationship between those different isolates and those patients. And here is the result of the sequencing. On the left, you have the global results, including the different the whole data set, including isolates from the outside and isolates from other units and isolates from our unit. And you can see that you have 3 different groups, and meaning that you have patients from the outbreak that have isolates from different groups. And if you go and if you zoom a little bit on the one on the bottom, you'll see that you have strains that have same sequence in the same patient, and the sequence is quite different from a patient to another. So the whole genome sequencing in our case allowed us to see that the strains were patient-specific. Also, we observed an increase of incidence in a specific area and a specific time frame, but the isolates were probably coming from the same environment. We did not find any environmental source, but in the environment they may be very diverse and present in terms of mixtures of genotypes, and then one specific genotype went to one specific patient, except for in here in green, where you see this genotype that has been found on patient 1 and patient 3. So these two patients shared one specific genotype. But patient 3 had also different genotypes associated to the case. So the lesson from this specific outbreak was to understand better the transmission of mucorcercinoides, and we used for that different strains from different time points from the same patient, and sometimes the same strain, different strain from the same time point in a given patient. And doing that, we had more chance to pick up isolates that were different in terms of genotypes, and to better understand the diversity of the population that gave rise to this specific outbreak. So in the end, the color here is specific for a specific genotype. You see that patient 1 and patient 3 are sharing one specific genotype, but for example, patient 2 had different genotypes compared to patient 1 and patient 3, meaning that we interpreted that as a mixture of genotype in the environment, and then the patient was transmitted a specific genotype that was able to persist on the patient, and sometimes in some patients, multiple genotypes that have been transmitted to the patient. The other example I would like to emphasize also is our first description of a transmission event in France in our center also of Candida auris. In the same unit in the burn ICU patient with a specific patient coming from Abu Dhabi with Candida auris. And we faced an alert of Candida auris quite soon after admission of this patient. And in the end, we observed later on, 61 to 41 days after the first case, we observed a second case of Candida auris in the same unit in a patient that have been tested negative at the very beginning, but was hospitalized at the same time than the first patient. And so the specificity here that we faced is a very long incubation period of the second patient when you analyze the first case and the possibility of transmission of this patient. So we investigate a lot the environment. We never found any Candida auris viable in the environment. We only found DNA. So I guess you discussed yesterday about Candida auris outbreak in Paris area using qPCR investigation. And so in our case, we were not able to find any viable Candida auris in the environment, or and we did not check any healthcare worker to understand if patients and if those people were transmitting the case to other patients. So we faced only 2 cases here, and then we had no other recurrence of Candida auris in our case. And so to prove that those 2 cases were linked in terms of microbiology, we did the whole genome sequencing. And based on the whole genome sequence of those isolates, we were able to find that these were coming from the same strain with less than 12 SNPs difference between the patient 0 and the strain of the patient 1. So in this case, we did not have in our hands other genotyping methods. Also now you have STR typing methods for Candida auris that can be useful to investigate rapidly the outbreak of Candida auris before doing whole genome sequence. So which strain to investigate based on our experience here in an outbreak? So you cannot investigate a lot, infinite number of strains. So you have to limit the analysis you can do. And yes, you don't have any infinite money to do that. So you have to limit your analysis. From what you heard, you have to use outbreak strains, but also locally identified strains that you can get from collections and also strains from other places. And then here you have the National Reference Center to help you to find and identify strains from other centers that could be interesting to be investigated in the same run, to be sure that of the diversity of the strain you can have on the national level. Then you can also investigate strains from invasive infections and also from the environment when it's relevant. And in our cases, it was relevant. And also, I would recommend to use different strains per patient, especially when you don't really know the pathophysiology of the disease, that have been collected either at the same time or over time, because it helps you to understand the dynamics of transmission and dynamics of contamination, and that is increasing the number of strains you have to investigate, but it gives you very interesting data to understand the dynamics of the outbreak. So to finish, I would like to conclude by saying that to respond rapidly to outbreaks, you need a structural laboratory, you need experienced people, and you need a lot of collaboration with hygiene people, pharmacists, clinicians, and you need the adhesion of clinicians to help you to investigate the cases, investigate the patients they have in their wards. You need weekly meetings to detect abnormal phenomena. That's very important. And if you don't do that, you will miss a lot of things. You need availability of genotyping methods. And you need a plan when you face this outbreak. And the plan is built with all the people from involved in the phenomenon. But this is a moving area, because the plan can be moving as long as the epidemiology and the incidence is and your investigation is ongoing. So with that, I'm finished, and I'm happy to take any question. Thank you very much.
So thank you very much, Alexandre, for your talk. Because of time, I think we won't have time for question, or perhaps only one, if there is one in the room. But because we have to move to the next communication. So thank you very much once again. And now it's my pleasure to welcome Professor Laurence Millon. She's a professor of medicine and medical mycology in Besançon University in the eastern part of France. Not so far from here, only 7-8 hours perhaps. And she will talk on the clinical surveillance and biomarkers. Thank you, Laurence.
So thank you, Jean-Pierre, for the invitation. So I will present these new tools for clinical monitoring of fungal exposure. To present this, I will talk about hypersensitivity pneumonitis, which are inflammatory interstitial lung diseases caused by inhalation of high quantity of antigens in previously sensitized patients. More than 200 causative antigens have been identified, mainly avian proteins, which are responsible for the most frequent HP, bird fancier lung. Other antigens are fungi or bacteria, which can cause farmer lung disease or domestic lung disease, and even mycobacteria that are found to be responsible for hot tube lung disease and mechanic lung disease. So rapidly, the antigenic proteins are inhaled and provoke an immune response at the low level at deep alveolar level, with antibody productions, which are immune complex that are deposited at this low level. This immune complex provoke inflammatory response and that cause symptoms, flu-like symptoms that are observed 4 to 8 hours after the exposition. So to investigate the etiological agents, the first step is a patient interview about occupational or recreational activities. There are investigations for the exposome of the patient by a microbiological culture from air sampling or from substrate such as hay, wood residue, or metal working fluids. And the other step is the serodiagnosis to look for specific antibodies against antigens that are really detected in the environment of patients. And this will be the focus of my talk. So serodiagnosis is part of a multidisciplinary approach which is necessary for HP diagnosis, which involve the clinical assessment, imaging, respiratory tests, and of course serology, along with bronchoalveolar lavage and sometimes biopsy, but these are invasive tests. Serology is non-invasive and allow to detect precipitin. So serology and microbiologic analysis of the source of exposure can help in identifying the causative agents and is helpful to propose eviction measure which is the only effective treatment for HP. So I will detail a bit what precipitation techniques are used, have been used for a long time. So the principle is semi-quantitative reactions that allow macroscopic visualizations of the antigen-antibody reaction by generating precipitation arc. So there are several techniques are in use: double diffusion, electrosyneresis, immunoelectrophoresis, and some others. All these techniques are non-automated. They are performed manually they are time consuming. It could take several days to get the result, and they require large volume of serum. And the precipitation arc are sometimes difficult to read and to count at the lab. So here you can see some examples. For example, double diffusion require 5 days to get the result on a high amount of serum. 300 microliters of serum are needed. For immunoelectrophoresis, it's also 5 days to get the result and a bit less serum. And electrosyneresis are more rapid. You can get the result in half a day, and you can use only 15 microliters of serum. To do these precipitation techniques, you need antigens. Two types of antigens can be used: total extract antigens, which are prepared by extraction of material manipulated by the patient. It could be hay, straw, or feather from a bird or metal working fluid, etc. So they are made up of variable mixture of antigens from bacteria, molds, mites, and others, and they are appropriated only for a first screen of global sensitization. Second type of antigen are somatic antigens, which are obtained from a single microorganisms isolated from the material manipulated by the patients. It could be either mold, bacteria, or other, and they are extracted from a pure culture. And the antigen are made up of mosaic antigen fraction from only one species. So they are a bit more standardized than total extracts. So in our experience, we use panels of antigens for HP serodiagnosis using precipitation techniques. We can use up to 6 antigens per panel. We choose the species the most often involved, and the panels could be different according to the type of exposure. So I will speak a bit in details about farmer lungs disease in next slides. So for domestic lungs, we use somatic antigens of mold selected after analysis of moisture damage dwelling in our region. So you can see the species we have chosen for this. And for mechanic slugs, for example, we also use somatic antigens from bacteria and mycobacteria and mold selected after analysis of metalworking fluids collected in car industry. We have Mycobacterium immunogenome and also some molds such as Fusarium. And in our routine test, we have been using for a long time 2 precipitation techniques, one first line with double diffusion and one second line with electrosyneresis. So you can see here example of result with a number of arc in the first line detection and the second line, and with several patients, either with mixed sensitization, actinomycetes and molds, or high sensitization with actinomycete here on the right. So this technique works quite well, but the lack of standardization. We use homemade antigens, and there are a lot of variation from one batch to the other. There are also variation for the reading and the interpretation of the arc. And with these techniques, it's really difficult to meet the criteria for accreditation. And another thing that prompted us to change our techniques was the discontinuation of material and reagents used for precipitation techniques. And especially, we don't find now cellulose acetate strips, which are necessary to do electrosyneresis. And there are also other reagents which are not found now. So just before going further, I just take a few seconds to show you this paper, which was published in 2005 by a consortium of expert pneumologists who listed the need and opportunities for research in hypersensitivity pneumonitis. And they highlighted that to advance in this field, the characterization of the offending antigens and the production of purified and recombinant antigens for developing new assays was necessary to really advance in this field. So in 2023, we had now new antigens, recombinant and purified. We have new techniques. For example, even commercialized techniques with immunochromatography and Western blots for avian HP. And there are some automated techniques, especially immunocapvadia. We talk about this morning. And I will now present you what we have done in our lab to develop ELISA recombinant antigens for new ELISA techniques. So I will talk about farmer lung disease, which is frequent in our region in eastern France, which is a cold and humid area with the production of Comté, cheese Comté. So this cheese Comté requires that cows are feeded only with natural untreated eye, which is a perfect niche for many fungi and bacteria. And so the prevalence is very is high in our region. So the first part of the development was the analysis, the microbiological analysis of eye and straw to identify the main ethological agents of FLD in our region. So that have been done during several years in our lab. And at the end, the main etiological agents was identified as actinomycetes, and especially Saccharopolyspora rectivirgula, on several molds, including Lichtemia corimifera, which is a mucorales also involved in a severe invasive infection in an immunocompromised host, and Eurasium amstellodami, which is an aspergillus from the Glogus group, and another mold, which is Wallemia sebi, very frequent in humid high. So the second step was the development of recombinant antigens specific of these main species that were identified. So we developed immunoproteomic approach to select the best candidates, and we also implement prospective studies for clinical evaluation of our new ELISA test. So quite several words about this immunoproteomic approach. We start from the culture. For example, here with Lichtemia, we did a protein extract, and we separated protein from this extract by two-dimensional gel electrophoresis. Then the gel was stained by Kumasi blue, and you can see different spots corresponding each to proteins. Then Western blotting was done using pooled sera of FLD patients to identify the proteins that was recognized by the antibodies of patients. So then the proteins that corresponded to antibodies was cut from the gel and identified using mass spectrometry to have the sequence of the protein. So for example, we have here a protein that is here detected by antibody and cut, who was a good candidate for our test. But you can see here proteins that are very abundant, but that are not detected by antibodies, and these proteins were not chosen for as good candidates. So, so we did this for Lichtemia, but also for Aspergillus glaucus and for Saccharopolyspora rectivirgula. So we identify many immunoreactive proteins that, and we choose the best candidate to be produced as recombinant antigen. When you have the sequence of the proteins, you can have the sequence of the gene. Then the gene is introduced in a plasmid, the plasmid in the bacteria, and with expression system, for example, of Escherichia coli, you can have many great amount of proteins. This was done. And in total, during these last 10 years, we produced 28 recombinant antigens from 3 microorganisms. So after that, we evaluated each of these antigen, of this new recombinant antigen by ELISA test using ROC analysis. And you can see here, as an example, we tested the 8 antigen issued from Lichtemia corymbifera. The best one was this DLDH with an area under the curve of 0.8, which was really good for us. So we did the same thing with the other microorganisms. And we finally selected 3 good antigens one for each of the main etiological agents. Then we we did several combinations of those the antigen, always with the aims to have the best combination of sensitivity and specificity for our test. We tried to do ELISA with 6 antigens, all those that we had in our precipitation technique, plus mixed of recombinant antigen and purified antigens, each associated with its species. And ELISA with 3 antigens. We did this in all the senses to try. And the best combination that was recently validated on a new cohort of farmers, lung disease patients on control was an ELISA with 6 antigens. But finally, we had nearly the same performance and even better for sensitivity when using only the 3 antigen, the main species, each associated with its recombinant antigens, like it is done in many commercial kits to associate the somatic antigen plus a recombinant antigen. So that was the best combination. And then to check, to optimize the global approach of our serodiagnosis of FLD, we combine this new ELISA test with double diffusion techniques that we used previously as a second line. And globally, this strategy gave us best performance with up to 90% of sensibility and specificity of 80%, and concordance of more than 80% with our previous strategy. But then using an ELISA techniques, which is less time consuming, which requires a few microliters of serum, and for which the result can be obtained in 1 or 2 days. So we have the same performance, but really with less time of working in the lab. So our project now is to do the same thing to improve the serodiagnosis of domestic HP. So we just have got funding from the ANSES to realize a case control cohort study with microbiological analysis in homes. So we plan to include about 500 patients with suspicion of domestic HP, to do environmental analysis using electrostatic dust collectors that are deposited in house for 4 weeks, and then we will perform culture on qPCR analysis on targeted species, especially involved in HP. And we also will implement blood sampling in patients to do serodiagnosis. The objective is to constitute an adapted panel of antigen for HP, home HP diagnosis, and develop new ELISA tests with recombinant antigen and eventually purified antigens. This will be done with 11 participating centers in France. So to finish, I would like to thank the collaborators in my team, and especially Coralie Barrera and Pauline Bélanger and Nadine Rouzet, who had prepared many of the slides I presented today. I would like also to thank Michel Monod, who was a key person for implementing production of recombinant antigens in our labs, and all the clinicians and mycologists who help us to collect serum and data to validate our tests. And I thank you for your attention.
Thank you, Laurence, very much for your talk, but also for all your valuable work, because it's now complicated with the industry of diagnosis. It is difficult to find some antigens to perform tests, so this is really important that you keep continue working on that topic. So, do you have question on this clinical surveillance? Yeah, Rina. That's good.
Just thinking that massive amount of work. Are you planning to? Are you working with a company, or is it going to be? At the end of the day, there's a massive need for this, and you've done the work.
Yes, we are in contact with a company for the recombinant antigens. We also have recombinant antigens which works very well for avian HP.
Yeah.
And we are in contact because it's more simple. We have only one antigen, which is really good.
Yeah.
So it's easy to implement in a commercial device.
Yeah.
For farmer lung disease, it was much more complicated, but because there are many combinations possible, so we only have the solution for 2 or 3 months. So it will be the next step also for farmer lung disease. But for avian, I think it will be done.
There's a big global market.
Yes, but not many patients, so it's not so. But
Not many positive patients, but we have. Yes, many have to be tested.
Thank you for your talk. I was wondering, in terms of the data that you generated, which I imagine is a lot, how is these type of data being shared nowadays? And for example, if I wanted to access your data, would it be available in some repository?
yes, all the protein we have identified are deposited in bank in several so the genome is protein. Don't remember the name exactly, but all are, and they are available in supplemental data of our publication. So
That's
you can
great.
write us. I can give you.
And you think it's common practice, or that's something still needed to be improved in this field in terms of sharing data and practices, protocols?
We can share.
No, if you think that it's been done by other groups also, just in general, your perspective.
For the avian proteins, there is a Japanese group who identifies the same antigen as us nearly at the same time. So it was good because we published, so there is no problem of patent or other because we published. So after, the difficulty is to produce the recombinant antigens, even if you give all. Yes, and this why Michel Monod was really a key person, because he helped us, because it's not so easy to produce a recombinant antigen. Even if you have all the the published data, there is some really.
Do you have a patent on it?
No, because we have published immediately, so it's not possible to have patent, but we can have contact with commercial company, even with
There are different types of. I am not a specialist in that, but I know there are different types of patents. Use patent and for the production patent. So
I had never understood how to do this.
Okay, so thank you very much. And now the last talk of this session. Is it working, this one? Yeah, thank you. So now, at this time of the meeting, it's time to go to practical approaches and routine to know what tools we have to use for the environmental monitoring. And these tools are different when the question is fighting against environmental infection in hospitals compared to in houses, at workplaces, or outdoor. And Rena, I like this morning your question. Do we need metagenomics to fight to monitor nosocomial infection in hospital? Probably not. So the question is where, when, and how monitoring fungal exposure. And of course, we have many tools to use. For example, when we want to look for molds, then we can look for spores, we can look for fungal fragments, and in this case, We want to know if we are faced to viable microorganism. And in this case, it is interesting to have microscopic tools, but also culture and sometimes molecular-based methods. We also have the possibility to detect specific fungal compounds, such as volatile organic compounds, mycotoxins, and even cell wall components, such as ergosterol, such as beta-glucan, etc. But as you know, they are everywhere. So how can we interpret that? And the fact is that when we are in a hospital and we want to have prevention of nosocomial infection, then we want to know if viable microorganisms are present. That means it's probably better to focus on the detection of spores and fungal fragments. When we are in other settings, in dwellings, in workplaces, or outdoor, then we want to have the entire photography of what is present. So we can use more refined methods, such as molecular methods, or mass spectrometry in order to detect mycotoxins, in order to detect volatile organic compounds, or even metagenomics. But indeed, the good question is the right method for the right question. And first, I'm going to focus on hospitals. So in hospitals, culture is probably one good method, because what do we want? We want to know if viable and life-threatening fungi are present. In this case, it is important to use sampling methods that will allow culture, for example, bioimpactors, to have air impaction, and then culture of viable and virulent fungi. So here the goal is really to evaluate the exposure to life-threatening fungi with a risk of infection, and even to detect multi-resistant organisms, and we have discussed on Aspergillus fumigatus resistant and Candida auris resistant. And usually, air samples are combined to surface samples, because air sample is only a photography of what happens during 1 minute, 5 minutes, or 10 minutes. And using surface samples, then we can have the history of what happened in a room regarding fungal contamination. But it's not so simple, because there are many air samples devices. And probably, the oldest of you know this Andersen device. That was the reference impactor device. And the fact is that there are also other techniques, such as filtration, such as centrifugation. We have evaluated different devices, and we have shown that new generation impactors, such as those who are here in this figure, are more efficient than the old Andersen methods. And regarding the culture media, this is also a question, and that's why we have sometimes very diverse results between countries, but it is because the techniques are far different. And you can see that if you use triptych soy agar here in orange or malt in purple, you can see that using selective poor medium to select fungi, then the efficacy of the sampling is higher. Of course, it is also possible to use molecular techniques, and to detect fungi using molecular tools, then it is not possible to use impactor air samples. So in this case, new devices using impingement are now available. This is the Coriolis that has been shown this morning, for example, for pneumocystis, because it's not a cultivable fungi. And here, there is a cyclonic sampling of all bioaerosols. That means with the same sample, you can detect spores, of course, but also viruses, bacteria, and pneumocystis. And what we have seen, we have compared, we have performed an interesting study in Nancy Hospital in the eastern part of France and in Rennes. And what have we seen? So the predominant fungal flora is composed by Penicillium, Aspergillus, Cladosporium, Alternaria. And besides, regarding bacteria, we have Micrococcus, Bacillus, and Burkholderia. As you mentioned this morning regarding the cystic fibrosis study, contamination is higher in summer than in winter. And there is also a highest fungal concentration in plaster rooms. Why? Because there is dust, because there is fine particles. And also in reception halls and in laboratories compared to patients' rooms and corridors. And regarding, with a wide point of view, the microbiological contamination, because we have met many correlations between different parameters, and there is one major correlation. The microbiological contamination link more closely to activities, human activities, rather than geographical location. Regarding bacteriological contamination, there was a significant relationship with humidity and no significant relationship with ambient parameters such as CO2 and temperature and presence of people, and no variation between the sample sites. And regarding fungal contamination, there was a significant relationship with temperature and humidity, significant relationship with optical particle PM10, and variation between the sampling sites and activities. And this was also observed in other publications. So sampling plan in hospitals is really important. We have seen during the presentation of Alexandre Alanio that it is important to have an algorithm with different steps. And sample in hospitals is not so easy because where can we sample? So the recommendation is to sample in protected area if we want to look for the prevention of nosocomial infection. Why? Because if we sample in a non-protected area, then we will find Aspergillus, then we will find some Fusarium and some other Cladosporium. And what do we do with that? So that's why in the plan for prevention of nosocomial infection, it is important to focus on protected areas, but with a rhythm of surveillance that is not standardized. And in France, we had some recommendation, and we proposed that rooms equipped with laminar flow system should be monitored once per trimester. And what is proposed is to sample 1 to 2 air samples under the airflow, and also 5 to 10 surface samples. Regarding the surface samples under the airflow, it is interesting to sample in the bedside table, telephone, television, technical book, because as you know, Aspergillus spores are electrostatic. And it is interesting also to know what happens outside the airflow with surface samples in the floor, extraction grid, and window sill. But however, it is also important to monitor in shared rooms of the ward and even in the corridors. And in Laurence Millon team, they have nicely showed that it is interesting to follow the fungal contamination in the corridors because it is a surrogate marker of what can happen in the rooms. But however, there is a need for international recommendation, and this is one goal of the end of this meeting. It is to go forward recommendation and standardization of the monitoring and also of prevention. Because we still have many, many questions. And what is a reasonable level of contaminated that is expected? So once again, regarding the French recommendation, we have considered that in the room with HEPA filtration, so laminar flow mainly, in the air, we accept 0 colony-forming unit of Aspergillus and even of other fungi. Similar outside of the airflow. And under the airflow, regarding surfaces, 0 colony-forming units under the airflow, but outside the airflow it is too complicated to have a sterile environment. So we consider that if there are less than 2 or 2 colony-forming units, then it is acceptable. And in the rest of the world, meeting room, airlock, corridors, etc., what we propose is to monitor during 6 months or 1 year in your hospital. Then you will know what is the baseline in your hospital, in your city, in your region. And what is expected is a low biocontamination, that means less than 2 or 2, the baseline defined for each unit. But because we consider that Aspergillus is the most life-threatening, then no Aspergillus. And regarding surfaces, low biocontamination, less than 5 colony-forming units, and no Aspergillus. But once again, this is probably far different between countries, and there is a need for standardization and for recommendations. Looking at other samples, because sometimes it is interesting, probably not in routine, but in different conditions, it is important to have a look of what happens, for example, in water. And we know that water can be contaminated by molds. And perhaps you remember this paper from Elias Anesi in 2001, and he said nosocomial aspergillosis is waterborne, with 21% of the samples that were positive. I remember at this time we performed a national survey in France, it was 1%. So it is far different between countries. Why? Because the water is not the same. Sometimes it's underground water. In other countries, for example, in Northern Europe, it is lake or surface water, and the contamination of this water are really different. And Elias Anesi, yes, so during these 3 years published in blood, then the 21% of prevalence. But it is not the same everywhere. So once again, it is important in each hospital, in each region, to know with a control sample what is the baseline of the contamination. And here you have some examples of papers looking at Fusarium oxysporum circulating in top water in French hospital. Here it was in Dijon, and also the last one of the last in Sardinia. What about food? So I don't know which speaker showed a pepper yesterday. Why? Because pepper is really, really very contaminated. And this was shown in the 20th century. And you know that when you have 1 gram of pepper, then you have 10.6 spores of Aspergillus. So it is massively contaminated. And some colleagues from Grenoble has shown in an old paper that different stuff were contaminated by fungi. And we have also examined different, evaluated the fungal burden in different meals in my hospital, in my previous hospital, and also assessed different disinfection procedures in order to eradicate Aspergillus fumigatus. So the problem in the hospital, this is in the routine context, but the problem is that we have also renovation and construction work. And of course, this is a massive cause of high fungal burden. And what are the objectives of the monitoring in this case? It's quite difficult because we are outdoor and there is a repercussion indoor, but what is the final goal? It is to evaluate and quantify the patient risk, and all patients are not at the same risk if you compare hematological patient or another patient that is not immunosuppressed. The goal is also to propose preventive measures, and when you give preventive measures to the direction of the hospital, then it is also important to evaluate the effectiveness of these measures. Not only to say you have to do that, but also to control and to measure if everything is okay. And sometimes in case of epidemics, of course, it is interesting to search for the origin of the nosocomial fungal infection. So what are the methods to monitor? It is important to have different steps of different checks. And the first one is not so costly. It is visual checks. It is also really important to check for the negative pressure in the construction zone, to perform particulate checks, and finally, to have the fungal biocontamination monitoring. Okay, so you see that we don't have only to focus on what will happen on the plate, but also to have all this view of the construction work. And beside environmental monitoring, then it is really important to have an epidemiological surveillance during the works, but now it is usual to have an epidemiological surveillance all over the years. Why? Because then it is possible to see the emergence of new cases and also in this case, as we have seen in the previous talk, to use molecular analysis of fungi. Regarding the methods, what is complicated is to know if a construction work is at risk, at high risk, or at low risk. And here, once again, we had a nice consultative work in France in order to try to classify the different works, the typology of construction work, and classified as high risk, moderate risk, and low risk. Because, of course, the surveillance won't be the same depending on the situation. And why? Because surveillance is costly. It's costly with consumables, but it's costly for technicians, etc. So we have to narrow, to choose the good, once again, the good monitoring in the good situation. And it is important to look at the risk inside, but also outside. And we will see in the next communication how we can prevent the spores suspension in the air. So I told you that one simple method is visual checks, and we have proposed standardized formula questionnaire to have a quick audit every day in the construction work. And what is important is also to propose frequency of environmental monitoring to be implemented, and who has to do that? Is it the lab? Is it hygiene service? Is it the direction? Well, so we have proposed that for visual healthcare unit, for visual it is the healthcare unit, for pressure it is the technical staff, for particulates it is the infection control team, as well as for airborne contamination and surface contamination. And here you can see that different frequencies are proposed in order to help these hospitals to implement the monitoring. And here are some proposed interpretations of the result of fungus according to French recommendation once again. And this is available online, but of course you will have access to this slide, so there is no problem if you cannot read exactly. But you can see that we have to distinguish patient's room in protected area compared to patient's room in other areas with no air filtration. And what is expected is different between air sampling and surface sampling. But you can see each time that regarding fungus, what is really important is to avoid the exposure of very immunosuppressed patients that are in a protected room with laminar airflow. We want no fungal spores and very few fungus in surface samples. And it is also possible to have investigation, and I like this paper, and Françoise Botrel was a part of this very nice and huge work in Lyon, in a hospital in Lyon. And here, in this case, the environmental surveillance allow the isolation of more than 3,800 samples. And you can see among them 394 isolates were Aspergillus fumigatus and were identified using molecular method and were typed. And here you can see that we are not going into details with the different clusters, but what was really interesting is that among the 234 genotypes, 7 clinical isolates shared genotypes identical to environmental isolates. So this is a good example of what can be done in terms of surveillance during construction work. So now if we move from hospitals to dwellings and to workplaces, then the goal is not the same. And that's why, looking at the sampling method, we will less use air impaction, but we will more use air impingement with using cyclonic centrifugation, and also surface samples, dust, because as you mentioned, Malcolm, dust, this is a treasure if we want to follow the fungal burden, and also electrostatic tissues. And here, in this case, it is interesting to use molecular tools. We can use also, of course, culture, but we want to detect what is the total flora, viable, but also non-viable. Because here, we want not to prevent infections, but to prevent allergies, particularly in asthmatic patients, particularly in COPD or CF patients. And what is really important to have in mind when we are going to give some advices for prevention is to know the abundance and the diversity of the flora more than the infectious risk. And in this case, there are two nice molecular tools that has been proposed. The first one is the environmental relative moldiness index, that is a DNA amplification of 36 targets. I'm going to show you what is it, and then metagenomics. So regarding the ERMI, it has been published by Steve Vesper, who is working at the US Environmental Protection Agency in Cincinnati. And you can see it is quite complicated with the formula. But what is important is to see that within the 36 targets, 26 are common fungi associated with water-damaged homes, and 10 are common fungi that are present in all homes because they originate primarily from outdoors. So we have worked in collaboration with Steve Vesper, and in homes from Brittany, we have shown a nice correlation between culture and between this ERMI scale. That means that these targets are also good targets for our studies in France, but Steve Vespers has worked with many countries, and we have also data from Singapore, from many countries, and it is a good panel, really good panel to study what happens in dwellings. Here you can see the list of all these fungi. And when it is important to detect this fungi, and once again, here is a work from a Besançon team, and it is interesting to see that some phenotypes of home phenotypes are more prone to be contaminated, and here in this case, some statistical significant results show that the living level, the house age, the heating mode, and also the presence, of course, of water damage are associated to high level of molds in houses. And here, This is evident, but it is important to say that, of course, dampness, odor, perceived humidity, steamed off wallpaper, and blistered paint are associated to molds. Why? Because this is associated to humidity in the dwellings. Another approach, another molecular approach besides the ERMI index is metagenomics. And here in this study, we have compared what happened in 15 dwellings of asthma patients compared to 15 controls. And in this case, we have used dust samples to perform metagenomic approach with 16S and 18S metagenomics using an Illumina MySeq. And we have shown that there are differences in terms of bacterial diversity and load in between the asthma patient dwellings compared to the control. But with some molecular signature, I won't say you the name of this of this species because it's quite complicated to pronounce. Cristalense Dermabacteriaceae. I don't have my glasses, so it's quite complicated. But so it's possible to have some signature of dwellings where asthmatic patients live. Regarding fungi, at the genus level, then we didn't have any statistical significant differences. But what is interesting is that some species were not distributed similarly between homes of asthmatic patients and homes from control. Finally, after hospitals and dwellings, the question is also in workplaces. And once again, the right method for the right question. But Raquel Sabino has given many information on that. It is important to monitor when some patients are sick because it is possible to give them a new job. Notably in France, you can benefit from a new job when you are when you have a disease, an allergic disease. And I took some examples, but we have discussed that regarding waste management. So in this case, some workers are really sick, and it is important to have an environmental monitoring, but also a clinical monitoring using serology, as you have mentioned. This is interesting because it is in groceries, and in groceries, this work was performed in hospitals. It is interesting to see that there is a risk for consumers, but also a risk for workers because they are more exposed to molds. And they used sampling methods with swabs for surface samples, and also different assays to detect microbiological communities. And what they have shown is that fruits and vegetables are the most contaminated area, with many molds such as Aspergillus, Fusarium, and also not only the mold, but also mycotoxins that were observed. And so it is a really interesting paper. Finally, I will finish with one slide on outdoor sampling. But Esther, you have discussed that this morning. Regarding outdoor sampling, as you know, many air samplings are performed. It is in most of the cases to see what are the aeroallergens, to evaluate the pollen exposure. Regarding fungi, there is one working group from ECMM and ISHAM that with the aim to evaluate the fungal exposure in sands and in water, so regarding recreational activity. And the results and the comments of this, the conclusion of this work was to say that Candida is an indicator of fecal pollution. This outdoor water can be also a reservoir of Candida auris, as we have seen, for example, in India. Aspergillus and Fusarium are everywhere, but also Demacia fungi and also dermatophytes. And what is really interesting is that we started this study in 2015, something like 16. And because one of us is involved in different WHO working group, it is the first time now that WHO has integrated fungi in the different in the guidelines on safe recreational water quality. So, because before, no data, no expected results on the potential contamination of recreational activities.
We have to mention João Brandão, because of regulation, that João Brandão from Portugal is really very, very active in pushing the subject of regulation. And if it will be regulated whenever, a big thank you should be said to him.
Yes, and he's the first author of this paper. That's why I mentioned it. So, I thank you for your attention. And you have seen that monitoring the environment is not so easy. Of course, we can see that it is simple. We want to know if there are fungus in the environment. But the problem is that we have to choose the good method for the right question. If we want to compare between countries, then we have to standardize. And after the break, we will see that we need also standardization and recommendation for remediation. Because when the results are positive, what do we do? In hospitals, in dwellings, and in workplaces. Thank you very much, and have a good coffee break. You have a question, Malcolm. Yeah.
Specific question. If you have patients in your hospital dying from cryptococcal meningitis, and there's a suspicion of pigeons roosting in the ventilation system, any sort of guidance about specific methods for monitoring the air and surfaces for crypto, as opposed to molds like Aspergillus?
So it is a rare event, but it is possible. So that's why there is no recommendation. But in case it occurs, then it is important to have some samples, surface samples near the windows, because pigeons, as you say, are coming. We have done that in Rennes for a few months because for another question, we wanted to work on the biofilm with between crypto, rhodotorula, and candida, and we never found crypto. But we know that we have cryptococcus infection, so yeah. But it is during a crisis meeting that we decide of what monitoring and what tools.
So, I mean, the background of my question is, and it's in the public domain, it's been in the international press. You know, there were 2 deaths from crypto in a brand new hospital in Scotland. So this has now become a massive inquiry. It's become very political. And there have been some papers published already, and the investigators did not find any crypto within the hospital environment, but they may not have used the right approach, the right methods. So that's the background to my question. Because perhaps the patient came with his crypto from his home, or yeah. It's not necessarily in the hospital that it was acquired.
And nobody kept the isolates, so you can do typing. So anyway, just a couple of comments. I think exactly agree. It's the same principle with any diagnostics. Don't do diagnostics if you're not clear what the result tells you to do.
Exactly.
So it's exactly the same here. I think the biggest problem we have, it's, you know, the black and white, the HEPA-filtered ICU operating theatre, 0 tolerance is good and easy. What happens at homes? Equally, don't know. If it's not black or mold, okay. But I think in our reality, the biggest problem is the part of hospital where you still have compromised patients, but they are not in HEPA-filtered rooms, they are, or when they come to outpatient visits, what standard do you have to have, let's say, in your radiology department, where the patient is in the scanner for half an hour,
Yeah.
and so forth, and sometimes somebody mentioned that the scanners are often in the deep basements of their hospitals, and
Yes.
and you know, what are they exposed to there? I think that is far more difficult area to agree to
Yes, indeed.
and discuss about the round table.
Yeah. Yes, this will be discussed as a preventive measures
Yeah.
with using masks and etc.
Yeah.
And but as you said,
And applies to pneumocystis and everything.
Yeah.
But the main comment I had about the home surveillance
Yes.
is that there are actually two. It's not only about allergy, it's about discharging your hematology patient back
Yes.
home after chemo, and then you do worry about infection.
Yes, and particularly nowadays with drugs such as ibrutinib, and patients
You go.
yes are out the hospital
Yeah.
when they are taking this such drugs. So very immunosuppressive drugs, and they are exposed because they are at home, they are gardening, they have some molds inside the house. So yeah, this is quite complicated.
So yeah, that's a double whammy.
Yes. Thank you.
Thank you so much. So in your presentation, you mentioned quite a lot standardization, and I'm wondering then what is missing to achieve that? Why are things not more standardized already?
I don't know, because I think it's the good time now to do that. You know, we have guidelines for diagnosis, guidelines for treatment, and now I think it's prevention is more and more important and more topic because of resistance, because of toxicity of drugs. If we look at what happens in US, perhaps you have the experience of what happens in US, but they say, okay, no problem, no matter with the environment, because we are going to give prophylaxis, chemoprophylaxis. But this was 10 years ago, 15 years ago. Now we know that with prophylaxis, we have drug-drug interaction, toxicity, and resistance. So it's far better to have prevention, prevent and not cure, or prevent or not prophylaxis. So that's why until now, many recommendations have been performed regarding the management of the patient, but it's a good time to do that for the environment. And that's why this meeting is the fungal exposome and health issue, and what can we do to go forward.
And so this is this higher body responsibility, or it's the whole community to agree on standards, or it's the World Health Organization that should standardize?
I think everybody is concerned, the patient, but also the government, politics, and also the director of hospitals. Because when I'm going to see and discuss with the director of my hospital, and I say, okay, we have to monitor, we have to implement some preventive measures, they tell me, okay, but this is costly, so not sure we can do that. You see, so we have to say to the director, it is your responsibility. When a patient is under a protected area with air filtration, it is a responsibility, at least in France, of the director to evaluate the quality of air. Similarly, it is the responsibility of the director of a hospital in France to have water supply of good quality. So when you discuss that with them, they say, okay, yes, perhaps we are going to have the good measure for prevention. And regarding dwellings, because this is a massive population, of course, and as I will show you in the next presentation, in Europe, usually moldy homes are between 20 to 40% in the different countries of Europe. So you see it's a huge amount of dwellings. So then it is the, how can I say, citizen responsibility and the mayor and the Ministry of Health to give some good advice to prevent and to say, take care, there is a risk.
The American
Thank you.
Green Book, which is in the US, there is the so-called Green Book, the recognition, evaluation, and control of indoor mold, where one of these really, really big indoor air society. So David Miller,
Yeah.
who's a proponent of this sort of thing, was telling me the other day there was a new edition of that standard, that green book coming out. And of course the WHO did in 2009, because I was involved in the book, Dampness and Mold, did not actually go into the depth of how do we standardize monitoring. It was more sort of the concepts and the background. But so yes, I think something is needed. And we have discussed this in ISHAM, having a working group on indoor mold evaluation. But
yeah, no, of course there are some initiatives with you said US, but in Canada also there is a very nice works in Germany, in UK. But the problem is that we are all different, so perhaps it is time to standardize between the different countries. Elizabeth.
Just a short question. When you propose Candida species as a marker of fecal pollution, human fecal pollution,
Yes.
Which species? All species or some species?
Yes, Candida albicans.
Yes. Okay.
Yes. Yeah, but it is similar to Escherichia coli, so that's why we consider that it is important to have both, not only bacteria. But yes, Candida albicans. Thank you for the question. Okay, so perhaps you want a coffee break. So, one more question. So,
I think just the other scenario that we need to is relevant here is that in Manchester we have a big maternity unit at a hospital which is now being rebuilt next door, and the old part of the hospital is like many old parts of hospitals, terrible. I mean, waiting for the dynamite, but we're not there yet. So what has happened that the water has leaked in this outpatient area where they do the scans for pregnant women, and that's where the outpatients are. And we have done monitoring of the air quality using our impactor. And we've never seen anything so moldy. It looks perfect. I mean, they've cleaned and, painted and, it looks fine. But it's like somebody put the impactor inside a compost. It's so moldy. And then they change ventilation, they change filters, they do X, Y, and Z, and it goes from bad to worse. And after a couple of months, so when do you blow the whistle and say, sorry, this is not, firstly, it's not acceptable as a working place for somebody to be there all the time. But secondly, pregnant women it's a specialist center, so they have HIV positive mothers, expecting mothers, of course, on treatment, hopefully with reasonable CD4 counts. But it's like, and then they say, well, this is a massive center. We see, how many 100 women a day. Where do we move these women? What do we do? We need proper rules and regulations so that also those of us who are in that position to say, you close down this building.
That's why I think experts must write something.
And it becomes medical legal if you don't say that.
Yeah.
The finger is pointing at you.
Yeah, completely agree. Yeah, thank you for these comments. Okay, so see you at 4:30 now.
Okay.